Every computing student encounters a specific sorting algorithm early in their training. It is rarely used in production, but its conceptual simplicity makes it famous. This is bubble sort. The name comes from a clear physical image. When you look at a carbonated drink, the lighter gas bubbles naturally rise to the surface while the heavier liquid settles underneath. Bubble sort treats data the exact same way. It looks at an unsorted list of numbers and forces the larger, heavier values to sink toward the end of the array, while the smaller, lighter values gradually drift toward the beginning. This process relies on a continuous sequence of simple, localized decisions. The algorithm works by examining just two adjacent items at a time, checking their relative sizes, and making a choice. If the item on the left is larger than the item on the right, they are out of order and they must change places. By sliding this two-element scanning window across the data, the algorithm slowly imposes order on a chaotic list. To understand how this works in practice, we need to look at the mechanical reality of how a computer actually handles a single swap. When we watch an animation of two numbers switching places, the movement looks instantaneous and effortless. In low-level computer memory, however, a direct swap is physically impossible without a safety mechanism. If you simply tell a computer to copy the value from position A directly into position B, the original value in position B is overwritten and permanently lost. To prevent this data loss, the algorithm relies on a temporary storage holder, commonly referred to in code as a temp variable. Think of it like swapping the contents of two cups. When you only have two hands, you need a third, empty cup to hold the first liquid temporarily. The swap happens in a strict three-step sequence. First, the value from the first position moves down into the temporary container. This leaves the first position safely available. Second, the value from the second position slides over into that newly vacant first spot. Finally, the value waiting in the temporary container moves up into the second position. The exchange is now complete and both pieces of data remain intact. Now that this fundamental brick of the algorithm is clear, we can scale this single swap operation across an entire array to observe a full pass. A single pass represents the complete journey of our scanning window from the very beginning of the array to the very end. Let us trace this step by step using a small sample array of 5 elements. The window starts at the far left, covering index 0 and index 1. It compares the two values. If the left value is larger, the three-step swap mechanism executes immediately. Once that choice is made, the scanning window shifts right by exactly one index position to compare the next pair. This step-by-step evaluation continues down the line. Even if the array starts out completely scrambled, this continuous shuffling produces a reliable mathematical outcome by the time the window reaches the final index. The absolute largest number in the entire dataset will inevitably get pushed along by the window, step by step, until it hits the final slot on the far right. Once it arrives there, it can go no further. It locks into its correct, permanent position. The first pass is complete. We have successfully sorted exactly one element out of 5. Because the remaining elements are still unorganized, the algorithm cannot stop here. It must reset and repeat this entire multi-step pass from the beginning. Repeating this process introduces a severe performance penalty, often described as hitting a quadratic wall. For an array containing n elements, the first pass requires n-1 comparisons to guarantee that the largest number finds its home. The second pass requires n-2 comparisons to secure the second largest number, and this pattern continues downward. If you add up all these operations, the total number of comparisons scales quadratically. This relationship is expressed in computer science using big O notation as O(n)(2). To understand what quadratic complexity means in the real world, consider how the workload changes as data scales. If you double the size of your dataset from 10 items to 20, the processing time does not merely double, it increases by a factor of 4. If you scale your dataset up to 10,000 items, bubble sort will grind through roughly 50 million individual comparisons. In stark contrast, more efficient modern sorting algorithms scale at a rate of O and log n, keeping their processing curves relatively flat as data expands. While bubble sort is fundamentally hindered by this steep quadratic scaling, there is an explicit optimization we can introduce to prevent it from wasting time on arrays that happen to finish early. In its standard form, bubble sort is completely blind to the state of the data. It will stubbornly execute every single pass and comparison, even if the array becomes perfectly sorted halfway through the execution. To fix this inefficiency, we introduce an optimization known as a swap flag. This is a simple Boolean variable that acts as a sensor during each pass. Before the scanning window starts moving, we set this flag to false, assuming that no swaps will be necessary. If the window encounters a pair that is out of order, the algorithm performs the swap and immediately flips the flag to true. However, if the scanning window travels across the entire length of the array and the flag remains false, it tells us something critical. Every single adjacent pair was already in the correct order. If no elements needed to be swapped, the entire array is completely sorted. By checking the state of this Boolean flag at the end of each pass, the algorithm can trigger an early exit, breaking out of the loop immediately and saving thousands of redundant operations. This simple modification gives bubble sort a best-case time complexity of O(n) when handling data that is already sorted. With the mechanics, the mathematics, and the optimizations established, we can reach a definitive verdict on bubble sort. In terms of sheer speed, its performance is poor, making it entirely impractical for industrial applications or large enterprise datasets. However, it excels in two specific categories: simplicity and memory efficiency. It is an in-place algorithm, meaning it requires virtually no extra computer memory beyond the single temporary storage variable we analyzed earlier. More importantly, its value lies in education. Bubble sort serves as the perfect introductory tool for software engineers to learn the mechanics of nested loops, conditional logic, and algorithmic efficiency analysis. It provides a visual, intuitive baseline that helps us appreciate why sophisticated sorting methods are necessary. It is not designed to be fast, it is designed to be understood.